This is lesson 5. We're talking about compound events, and it's our final lesson in Unit 12. We're going to look at a simple event where you have an event that describes a single outcome, and we'll also look at some compound events. That would be an event made up of two or more simple events. We also have mutually exclusive events. That's when two events cannot happen at the same time. When we have two mutually exclusive events, we'll call them A and B. Then the probability of A union B is the probability of A plus the probability of B. And an example of that would be when you're rolling a die, the probability that you get a number less than 3 would be the probability that you roll a 1 or you roll a 2. So the probability of rolling a 1 is a 1 in 6 chance, and a probability of rolling a 2 is also 1 out of 6. So 1 out of 6 and 1 out of 6 is a third of the time. So 2/6 reduces down to 1/3. An inclusive event would be when you have two events that have one or more outcomes in common, so they overlap. The probability of two inclusive events, A or B, occurring is the sum of their individual probabilities, but we've got to subtract the probability of both things occurring. So here's our process for that, and an example. When you're rolling a die, what would be the probability that you get an even number or a prime number? So an even or a prime, when you think of getting an even, we're thinking of the numbers 2, 4, and 6 on one single die. But when you're thinking about a prime number, you've got to consider the overlap. 2 is a prime number, 3 and 5. So the even numbers are 3 out of 6 for that probability, the probability of an even. And the probability of a prime would be 2, 3, and 5. So again, 3 out of 6. But we've got to consider that overlap. And we have an overlap when the number 2, which is both even and prime. So there's one number out of 6 that is common to both events. So 3 out of 6 and 3 out of 6 minus that 1 out of 6 for the overlap gives you 5 out of 6 probability. Now let's go on to example 1. Are the events below mutually exclusive, and explain why or why not? So in A, we want to roll a 3 or a 4 on a number cube. So rolling a 3 is different than rolling a 4. We could say, yes, these are mutually exclusive. And the reason why is rolling a 3 is different than rolling a 4. In part B, we want to know rolling an even number or a multiple of 3 on the die. So we got to think of the sample space in each case. So the even numbers, I'm going to say no, because the even numbers 2, 4, and 6 are even, but multiples of 3 are 3 and 6. Those are multiples of 3 on the die. So we have a common outcome of 6 in those two sample spaces. They are not mutually exclusive because of that common outcome. On part C, rolling a prime number or a multiple of 4 on the die. So the prime numbers are 2, 3, and 5, and a multiple of 4 would just be the number 4. So we could say, yes, these are mutually. So our prime numbers are different than 4. Then part D, in a deck of 52 cards, we're wondering if drawing a red king or a black king are mutually exclusive. So in that case, I would say yes. A king is either going to be red or black. So they don't have an overlap. And part E, each student can vote for president of student government. 32% voted for Sparks, 28% voted for Kolb, and 40% voted for Ramos. Well, every student can only vote one time, so yes, this would be mutually exclusive because of that fact. Every student is allowed one vote. And next we're going to look at probability of mutually exclusive events. In example 2, a group of students is donating blood during a blood drive. A student has a 13 out of 30 probability of having type O blood, a 6 out of 15 probability of having type A blood, and a 2 in 15 probability of having type B blood. What is the probability that a student has type O or type A? Writing out that probability, the probability of a type O or a type A is the probability of O plus the probability of A. There's no overlap in that case. So 13 out of 30 for type O and 6 out of 15 for type A. So we have a 25 out of 30 probability, which is a 5 in 6 chance of having type O or type A. And remember here, I'm making my common denominator 30. In part B, what is the probability that a student has type A or type B blood? So the probability of A or B would be the probability of A plus the probability of B. So the probability of A was 6 out of 15, and the probability of B was 2 out of 15. So that gives us an overall probability of A or B as an 8 in 15 chance. In example 3, we see we have a deck of 52 cards, and we need to know what the probability would be if you chose a king or a queen. So the probability of a king or a queen would be the probability of the king added to the probability of a queen. And remember, in a deck of cards, there are 4 suits. So we have 4 kings out of 52 cards and 4 queens out of 52 cards. So that gives us a probability of 8 out of 52. And if you simplified this by dividing each numerator and denominator by 4, we would see that probability would be 2 out of 13 in simplest form. Next, we want to consider the probability of inclusive events. So this is when we're looking for the overlap. Let's say you have a card and it's drawn randomly from that deck of 52 cards. Find the probability that you're going to draw a queen or a heart. So this probability, we've got some overlap. The probability of getting a queen or drawing a heart out of the deck, remember there would be a queen of hearts, and there would also be 12 more cards that were from the heart suit. So we've got to think of the probability of the queen plus the probability of the heart, and then we're going to subtract that we had the probability of a queen plus a heart. So remember, there are 4 queens in a deck of cards, and the card deck is 52. So 4 out of 52 is the probability of a queen. There are 13 cards that are hearts, which includes our queen. So we've got to subtract out the one overlapping queen card because it's already in this 4 out of 52. So this is 4 plus 13 minus 1. That's 16 out of 52, which is a 4 in 13 chance of drawing a queen or a heart. In part B, drawing a black card, which is the spades or clubs suit, or drawing a face card, which is a jack, queen, or a king. So the probability of getting a black card or a face card would be the probability of the black plus the probability of the face card minus the probability of the overlapping, so I'm going to say of both. So the black cards, there's 2 suits that are black, that's the spades and the clubs, so 13 spades and 13 clubs gives us 26 out of 52, that's half the deck. And then the face cards are jack, queen, king, but there are 4 suits that have jack, queen, king, so 4 times 3, that would be 12 cards out of 52, and then the overlap would be 6 out of 52 cards because there are 2 suits, spades and clubs, that are black face cards. So 6 out of 52. So 26 plus 12 minus 6 would give us 32 out of 52 for the probability, or simplified, that's an 8 in 13 chance of drawing either a black card or a face card. In example 5, we want to find the probability of rolling an odd number or a number that's greater than 2 on a number cube. So our probability of rolling an odd or a number greater than 2 would be the probability of the odd plus the probability of a number greater than 2, and we're going to subtract the probability that it's both odd and greater than 2. So our odd numbers would be 1, 3, and 5, so that's a 3 out of 6 chance. A number greater than 2 would be 3, 4, 5, and 6, so that's a 4 out of 6. And then odd and greater than 2, those would be the 3 and the 5, so they have 2 out of 6 that are the overlap. 3 plus 4 minus 2 would be 5 and 6 chance of having an odd number or a number greater than 2 when you rolled your number cube. In part B, we want to roll at least 1 5 when rolling 2 dice. So we have the probability of a 5 or the probability of a 5. So the probability of a 5 plus the probability of a 5 minus the probability of a 5 and a 5. When you're rolling 2 dice is you've got a 1 in 6 chance of rolling 1 5, a 1 in 6 chance of rolling in 5 on the other, but then you have 36 as a sample space of rolling a pair of 5. So a 1 in 36 chance that you would roll a pair of 5s. So 2, 6 minus 1 out of 36. 2, 6 would be a 12 in 36 minus a 1 in 36. So there is an 11 out of 36 probability of rolling at least 1 5 when you're rolling 2 dice. In a survey of 1,600 high school juniors and seniors, 860 were seniors, 650 watched the evening news. Only 225 of the evening news watchers were juniors. What's the probability that a student was a senior and watched the evening news? In this case, I want to make a two-way table. So let's think. We've got the seniors and the juniors. We have seniors and juniors. And we have yes, they're watching the news, or no, they're not watching the news. So our seniors, they said 425 and 225 would give us the 650 total. And no, they weren't watching the news, so we had 435 to give us 860 total there of seniors. And that would leave 740, so this would be 515. And then this first row is 650, the second row would be 950, and that would give us the 1600 in both cases. So if I treat my survey like this two-way table, these are the people watching the news. Write that sideways. And we want the probability that they were a senior or they watched the news. So we have 860 plus 225 divided by 1600, which would give us 1085 divided by 1600 total, which is about 67.8 or 60.6781 or 67.8% of the students that were seniors. So seniors 860, or they watched the news, which would be the 225 juniors. So 860 plus 225 divided by our total would be that 67, almost 68%. In example 7, we have a total of 880 customers at the Xanadu Day Spa. 92 had scheduled a massage and 63 scheduled a facial. There were 26 who only had a facial appointment. What's the probability that a customer had a massage or they had a facial? So we've got to consider the overlap in this case. So we have both, and we have a massage, and we have a facial. So they told us that there were 92 that had a facial. 92 that scheduled a massage, and 63 had a facial, and 26 had just a facial. So that leaves 37 that did not, and that would be 37 that had both. So we have 55 having the massage. So in this case, we have 92 out of the 180 plus 63 out of the 180, but the overlap would be 37 out of 180. That leaves us with 92 plus 63 minus 37, or 118 out of the 180, which can be simplified to 59 out of 90. So we're looking at about 0.655. The probability that a customer had a massage or a facial is about 65.5%. And then in our next example, we have a school survey of 100 students. 46 are female. 58 are in favor of changing a schedule from a 7-period day to a 6-period day. Of those in favor, 22 are male. 1 student is picked at random, and we want to complete the Venn diagram at the right. So in our Venn diagram, we had 22 are male and 46 are female. So we would have, 36 and 10 to give us 100. Let's see, 100. So you can see where I got the 58 in favor would be 36 female and 22 male, so they agree. And 10 and 36 would be our 46 females. And we want to know on part B, what's the probability that the student is female or they favor the change. So the probability would be they're female or they favor. So we've got to consider the overlap here. So female is 46 out of 100, and they favor is 58 out of 100. Then subtracting the overlap would be 36 out of 100, which gives us 68 out of 100, or 68% would either be female or they favor the change. Part C, what's the probability that the student is male or they oppose the change? And they had us 54 out of 100 plus 42 out of 100 minus 32 out of 100. And looking at my table here, we know that 10 females don't agree, and there's 32 people left over out of the 100. That's where we got the oppose. The 54 for the students that are male would be from 54 and 46 give 100. And then the 32 that oppose are the overlap there. So that leaves us 64 out of 100, or 64%. So we had 54 that were male, 42 opposed, and 32 had both in the overlap. And then our last two examples. Remember that the complement of an event with probability P, all outcomes that are not in the event has a probability of 1 minus that outcome. You can use the complement to find the probability of a compound event. And in example 9, in one day we have 6 different people bought purses from Macy's. They offer 48 different purse styles. We want the probability that at least 2 people bought the same style purse. Here you can see I've listed out my thinking. We want the probability of at least 2 people choosing the same purse. That can be figured using the complement by saying 1 minus the probability of everyone choosing a different purse. So this is called the complement, which we saw up here. And the probability that everybody chooses a different purse can be found by considering the number of ways the purse can be chosen divided by the total ways that 6 people can choose that purse. So we saw this earlier. That's a permutation of 48 items taken 6 at a time. And every time somebody chooses, that's 48, 48, 48. So we've got 6 people. And if we expand that out, 48 times 47 times 46, 45, 44, 43, you can see there's our 6 people choosing. And dividing by 48 choices each time leaves us with this calculation. Now on my calculator, that has worked out to a very large number divided by another very large number, or if I get the decimal value, that would be 0.722409. So our complement of the event, 1 minus the probability, is going to be 1 minus 0.722409. So we find that that's about 27.8%. So 27.76% of the time you'll have at least 2 people buying the same purse. In our final example, it's similar to example 9. So we have the probability of a vending machine offers 10 different drinks, and one day 5 employees each purchased a drink from the machine. We want to find the probability that at least 2 employees purchased the same drink. So we've seen in this lesson that the probability of an event happening plus the probability of its complement, that is, the event not happening, that has to total 100%. And this is how we found out that the probability of the event for example 9 occurring was just 1 minus the complement, the probability that the event didn't occur. So here in example 10, we have 10 different drinks. So we want the probability of the number of ways 5 employees can choose the drink. So that's the probability of 10 choose 5 divided by the 5 choices, or 10 to the 5th power. So this would give us 10 times 9 times 8 times 7 times 6. There's our 5 employees. And we've got 10 times 10 times 10 times 10 times 10. We can eliminate 2 of those 10s. And then 9 times 8 times 7 times 6 is 3,024. And we've got 10 to the 4th power. So 10,000, which gives us 0.3024. So to find the probability that at least 2 employees purchase the same drink, the probability that at least 2 choose the same is 1 minus the probability of not choosing, not the same. So 1 minus 0.3024 tells us that about 70% of the time, or 69.76%, at least 2 people are going to buy the same drink. And here we are at the end of chapter 12.